Well, good evening. It's Sunday night here in Seattle, and I wanted to just take a quick play in the lab and check a piece of gear that I bought, but I hadn't put on the bench yet. You know, the Seahawks had just finished playing, and uh, I was just wrapping up for the day, and I thought, better get this out of the hallway, before my wife's patience wears too thin, and give this a test and see if this actually works. Now, this unit here is an 8757D scalar network analyzer. Now, scalar network analyzers differ from vector network analyzers in that they consider amplitude only. They're not looking at the phase of the signal. So all of that information that you gain from a vector network analyzer by being able to understand the phase of the signal, you don't get that with these units. But what you do get is the ability to make measurements that are scalar or amplitude only very, very easily. So rather than using tracking generators and standalone directional couplers and power sensors and all this sort of stuff, what I can use is basically this unit and these items here. The 85025A detectors, which detect the power, and the 85027C directional bridge. And this will detect the power as well from a directional bridge inside this unit and return that to the scalar network analyzer. Now, I hadn't bought one of these because I've been hanging out to see if I could find a 20 gigahertz vector network analyzer, something like an 8720D or so on, at a reasonable price. And I haven't been able to find one of those. So on the groups.io HP or the trader group, a ad was posted, or an email was posted saying that one of the guys on the group had these 85025A detectors available, and they were new in box. They had never been used. They're still sealed in the original HP wrapping. And so I thought, well, great. The biggest challenge with buying these things I've seen is that these detectors are hard to get and hard to get to know that they actually work and they haven't been affected. And so these for a really good price. So I went out and I bought the cheapest, good-looking 8757D that I could find. And while I was at it, I also noticed a guy selling the 85027 directional bridge for a reasonable price as well. So I thought, well, I'll just pick those up. So now I can take those scalar measurements across the entire range. So one of the measurements that we can do is of something like my, if you can see it here, might be easier to see it under this guy here. This is the 8491B attenuators. Now I have the attenuator set, so the 3, the 6, the 10, and the 20. This is the 10. You can see, if you look closely, this is the calibration information that was provided originally. Basically, this sticker stuck there and somebody got a hot pin. They measured this on the original test equipment, and then they basically stuck this pin in here at all these spots to get the information. And in fact, if I go to I think I have it here, you get, these aren't the right cards, these are for a different item, but you can see the calibration report, and they measure a certain set of frequencies and telling you what the reflection coefficients are and so on. And so I have a full set of these, and I can use this tool here to go and test that. So let's plug this in and turn it on and see how it goes. Now, I've already connected up the system interface. These have a system interface that will drive this and the sweep generator together, so they become one unit. It's actually pretty cool, and I'll show you that, where you can use the keyboard or the user interface on the the keypads on the controls on the front of the sweep generator, and the scalar analyzer understands it. So what we're going to go do is basically measure the attenuation of this device here and see how it goes. So to do that, what I'm going to take is I'm going to take my 11667A, I got to look at the right camera to make sure that you guys can see it, power splitter. Now these are pretty good power splitters. They'll split the power coming from my 8340 in half. Let me just get that cable laid out. And so now I should get the same power on each of those outputs. So the first thing I'm going to do is hook in a hook in the second, or the reflection, or the ratio measurement, which is the R channel just here. So let's take this, and we'll drop this in here. And these have a cool little locking nut type thing. It's a bit of a pain to get off. We'll take this. You can hear it. I don't know if I mentioned this already. The drink of choice this evening is a new half strength coffee. It's not a decaf, it's a half strength coffee. And I'm actually doing it in my original Windows NT Team mug from way back in the days. The coffee's pretty cool. I found this mug in my garage when we were cleaning up, and I thought, well, let's get it on the bench and use it. It goes with the whole theme of using old gear. Anyway, half strength caffeine coffee. Not that bad. Okay, so now that we've got the reflection measured up, what I'm going to want to do is also connect one to the other side, and this is actually going to be the incident, or this is going to be the detector that will go with our device under test. So let me just screw that in and get that out of the way so that you can see what's going on. We'll take that cable. These are all brand new, so they haven't yet worn in. Let me make sure that my coffee is not going to fall off the table here. Can I keep that? Is that going to stay in sight? So that you can see what's going on there. All right, and now I'm going to stick this into the B port, and we're going to take basically that ratio measurement from, this side's going to come into, this is going to go, let me make sure that I've got the right into the B port, and then we're going to place our device under test in between here. So let's turn the unit on. And the process that you normally go with these is you select the channels that you want to use, you set the frequency range and the power that you're interested in, then you do a calibration, and then you do your measurements. So here we can see that we've got our signals coming across. You can read the signal coming in here, and there's a signal in here, and we haven't set up a measurement yet, but what you may notice here, and let me zoom in on that. Okay. All right, back now. So I've forgotten where we were. Anyway, let's just hit preset. Okay, so what you can see here is we have our two signals, two channels, and so channel one is measuring A, which has, let me zoom back out a little bit, is measuring A, which has nothing connected to it. Channel 2 is measuring B, which has the detector connected to it, and that the device under test is going to be, and then R is a standard measurement that's measuring the signal that you're inputting, so it can do the ratio measurement there. Okay, so the standard order that you go through when you set these things up is you hit instrument preset, it restarts the instrument. Then you select your measurement, the channel you want to make, that you want to watch. Then you set up your signal source. Then you calibrate, and then you can save that calibration if you wish, but then you basically take the measurement. So in this particular case, what we want to do is we have our thing in channel B, so our measurement is going to be a ratio of BR. So we're going to select that, and then what we're going to do is turn channel 2 off. So on channel 1, we're measuring BR, and you can see that there's, if we zoom in on the scale, let me zoom in on the scale. You're not really seeing it. Now you're starting to see it. You're seeing the, there's some dodgy parts of the signal. It's up and down. We want to get rid of that. So let's start that whole process again. What we'll do is we will come in. We're going to set up our measurement. We're going to do BR. We're going to get rid of channel 2 because we only want channel 1. Now, and this was the cool thing I was talking about with the system acting as one individual unit. I'm going to come over here and I'm going to set the stop frequency to be 18 gigahertz. And you'll notice if we zoom in again, that now it's changed to 18. If I went back to stop frequency and set 25 gigahertz, you'll see it change there. So that's pretty cool that the systems all work together in as one sort of big virtual instrument. So now that we've done that, we want to calibrate out those little bumps. And so to get rid of those little bumps, we're going to calibrate and we're going to select through because we're just looking at the straight amplitude. And we're going to already connected, so we'll just store our through. So now we're stored and I can save that to register 1. And now we're completely saved. And you can see that we've got a perfectly flat line there. That's great. Now, what we want to do is go in and add our device under test. So to do that, what I'm going to go do now is select this guy here. We'll take this guy off here. And then we should see this thing drop way down. I'm going to put our 10 dB attenuator on. And then we're going to connect our detector to our 10 dB attenuator. Get it nice and tight. There we go. And now we're measuring. So if I put our cursor on, what you'll see, as you can see here, is as I move the cursor, let me see, so as I move the cursor back and forwards, you can see the cursor value is minus 9.8, minus 10, sort of thing. It's moving around a bit. So if we do a scale now, and we say auto scale, now you can see how it's actually working. So, let me do auto scale again. So you can go back to cursor. You can see that now as we move back forwards, you might be saying, wow, look at that, that's all pretty horrible. Can we scale that down again? No, I think if we scale up, enter off, and then auto scale again. No, oh, here we go. Anyway, you might be saying that's pretty horrible, but if I grab my little printout of the actual values here, for the 10 dB guy, from 0 to 12 is 0.4 of a dB, and from 12 to 18 it's 0.5. So given that that's the reference line in the middle there, I must have bumped this. Given that that's the reference line in the middle there, that's probably pretty good. We can make it even easier. Imagine if you were testing a bunch of these things, what I can do is I can go into special and I can enter some limit lines. So I'm going to enter a flat limit line, and I'm going to say from 0 gigahertz, what was it? It was 0.6 dB. Let's see, what am I measuring? The 10 dB one? Yeah, for 10 dB, it's 0.6 dB from DC at 18 gigahertz. So now the upper value, because remember, we're reading the signal as it's coming from the bottom, after it's already been subtracted. So it's supposed to be 10 dB plus or minus 0.6. So the upper one is going to be minus 9.4. Enter. Oh, sorry, let me do that again. So we're going to enter a flat line. Frequency is 0 gigahertz. The upper is going to be minus 9.4 dB. The lower is going to be minus 10.6 dB, and the upper frequency is going to be 18 gigahertz. So we're done, and let's turn our limit lines on. And let's turn our scale down so you can see the limit lines. And there you go. You can see now how the system that is showing where the attenuator should be within that band, and it's telling me whether I'm passing it. Now, right down the bottom here at very close to 0, we're getting at 10 megahertz. I'm having the system go unleveled and stuff. So, all right. And so now you can, well, as I was saying, this I've got problems with it. But you can see that the pass mark, so if I was going in, and let's say, you know, I added I took a different attenuator, out, and I grabbed, say, my 6 dB and put that on. And auto scaled again, and then scaled that down. You'll see that now we're out and we're getting a fail all the time, which is what we would expect. So the next type of actual measurement we could do is we could say, well, let's add that measuring this guy to SWR as well. And to do that, we're now going to introduce our bridge here. So let me take this off and just sit it over there for the moment. We'll take this guy off. Won't need that again. And now what we're going to do is put our little coupler on. And we're going to take this guy and hook it in here. So now what we've got is the power coming in being split to two parts. This is the reference detector. This is coming into the directional bridge, and the device under test is going to go there. So with that, what I'm going to do is put this in here, and now we can do a multi-channel thing. So we can now look at not only the amplitude of the system, let me come back there for a bit. We can look at not only the amplitude effects of the attenuator, but also SWR. Okay, well, let me hit preset because we'll start this whole thing again. But what we're basically going to do now is measure SWR, being the reflected stuff coming back in on that channel A, and then on channel B, we'll measure the straight through. So the first thing that I need to do is, because this is a reflected measurement, we need to do a calibration. We need to set our measurements up. It's actually the first thing we need to do. So let's see, what do I want? On channel 1, we'll turn channel 1 on. We're going to do, our measurement is B versus R, which was that amplitude. And on channel 2, we're going to do A versus R. So we're going to look at the reflected information that's coming in here from the directional bridge. And we're going to want to display that in SWR rates. So now what we're seeing is the power that's coming through off this detector here, and we're seeing the reflected information. Now, because this is a reflected item, I'm going to have to go in and do a calibration. We're going to do channel 2. I'm going to connect our short. So I've got my Hewlett-Packard 85032E calibration kit short here. So we'll drop that on there. We'll store the short. Now we flip it around and we store the open. So there we go, we store the open. And then on channel 1, I'm going to need to, and I think you have to swap it to channel 1. You might not have to. But we're going to do that on channel 1. We're going to go do and store the through. Okay. Well, let me grab a little more coffee. That was clearly a problem. I just redid the whole process again. I think I must have gotten confused with what channel I was on. Anyway, if we select channel 1, which is our attenuation with our cursors selected, you can see that it runs between, you know, minus 9.8 and you know, minus 10. So now if I went back in, what was that spec again? It was going to be plus or minus 6 dB. So if we come back to special, enter our limit lines here, that should be fine. So if we turn those limit lines on, and then we scale it down a bit, there you go. You can see the attenuator is sitting nicely within the limit lines there. Now, what I can do is I can set the ref position down a bit. So we'll put that down towards the bottom there. And then we'll go to channel 2. And the SWR breaks up into 3 for channel 2. So let's go enter those in as well. So the first line is going to go from, let me make sure I have the right one. It's going to go from DC, so 0 gigahertz. The upper SWR should be no more than 1.2. Enter. The lower SWR is going to be 1, because if it was perfected to be 1. And the upper frequency is going to be 8 gigahertz. Then the next line is going to start at 8 gigahertz. And the upper SWR at 8 gigahertz is going to be 1.3. The lower SWR is going to be 1 again. And that tops out at 12.4 gigahertz. And then the upper band SWR is going to be 1.5. So we're going to create another flat line. We're going to start at 12.4. Then we're going to say, 12.4 gigahertz. And then it's 1.5, enter. The lower is 1. So there we're done. And that's 18 gigahertz. So there we're done. So let's go back and let's turn those limit lines on. Let's go to scale. And then we'll choose ref. And we'll move that up a little bit. Let's go to channel 1 ref. See if we can move that down a little bit more. Channel 2. I think we're going to have to turn the scale down a bit more. And then reference. Oh, no, it can only go up to reference 1. Oh, let's reference position. There we go. Okay. So what we're seeing here is that for my 10 dB attenuator, we are passing on its attenuation across that frequency band, and then we're also passing on the SWR. And if we come back to our cursor, we can see what the SWR is at any of those points. And we say, okay, well, like my worst attenuation is going to be at 13.4 gigahertz, and it is going to have an SWR 1.3. If I change over to 1, it's going to say it's minus 9.6 dB. So what I could do now is I could actually print that out, and then I would have an actual data set that would tell me for whatever frequency what my attenuator is doing. Anyway, what this is showing me is that the gear is probably working. Now it needs to, as I said, the 8340B, as you can see it by that peaks that I keep getting down the bottom here, is clearly going unleveled and needs to be fixed at some point. I'll get to that. It's on the whiteboard now. Anyway, I think the gear is good. I think the detectors are pretty good. This will go into my rack on the far side. Anyway, I hope you found that interesting. And if you did, give me a thumbs up. And I'll see you in the comments. Catch you later. Bye.